Oh, very warm welcome to all participants of our 2 days online seminar. Topic we're talking about is Inspect Before Connect, the side aspect of the fiber optic testing. My name is Alfred Huber. I'm the technical head of the technical department of Softing IT Networks, and I will guide you to this little webinar today. I'm not alone doing this. I got a colleague who is supporting me in the background. So if any questions are raising during the presentation, do not hesitate with the questions, just type them into the question field. And my colleague Matthias, who is in the background, will directly answer the questions. And later after the presentation, we will discuss the questions and answers on this as we used to do. So what we're going to talk about today, it's a topic which is very important on the fiber optic testing. It's called Inspect Before Connect. It means inspecting is fiber optic connector end phase inspection, and cleaning is the key to error-free data transmission. A little topic which is not always represented properly, but it's very important in the world of fiber optics. Before we start to talk about the topic today, let me quickly introduce Softing. Who is Softing? The people who are not too much aware of what Softing is doing. Softing is a mid-sized German-based organization company. The headquarters is near Munich. The company was founded in 1979, went public in the year 2000. Last year's turnover was about 90 million euros. We share about 400 colleagues, and we got local presentations all over the world, as you can see from this little list. Softing basically is divided in 3 business units. The main business units are the automotive stuff and industrial stuff. What are these colleagues doing? Automotive is providing solutions for ECU diagnostics in automotive and cars and so on. So providing testing system for the control units of cars. The industrial automation colleagues, they are providing products for the industrial production environment. It's mostly kind of gateways to let machines talk together, speaking different protocols, different languages, to make them possible to communicate. Our colleagues providing solution on this. Also, a new area where they're working in is collecting data from machines and do some preventive maintenance on these things. Our part, IT networks, as you see, we're sitting in the middle of these little temples. So our job is to provide test and measurement equipment to verify, qualify, or certify copper or fiber optic transmission links, wirings. So we are coming usually from the building cablings. So we were acquired by Softing in 2014. Our previous name was Cyber Data. We changed the name in 2016 and now are working with the name Softing, or known as the Softing IT Networks. What do we have to do with automotive and industrial? There are tendencies in the industrial world to move away from all these bus systems, the field bus system, Profi bus, whatever bus systems you know in the industrial world, to move to Ethernet. The Ethernet protocol to be the carrier for industrial communication. Similar things are happening to automotive. So cars are usually using the CAN bus for communication within the car itself, and very slow bus, let's say. And these kind of buses are going to be replaced as well against these buses are going to be replaced again with Ethernet buses. So Ethernet will be the future protocol in these 2 worlds as well, automotive and industrial. And if Ethernet is moving into one of these worlds, it's also bringing its own cabling system with it. And in the Ethernet topology, the cabling has to be separately tested from the application, which is in a field bus system not the case. So everywhere where Ethernet moves in, you also need to move in with test equipment for the Ethernet cabling structure in the background. So this is why we are sitting very prominent in the middle with providing test equipment first of all to the building cabling systems, then to the industrial automation industry, and to the automotive industry. So this is our position, our role, why we're sitting here in the middle in the softing. Where are we on the world? Where are we spread on the world? Let's see. Let's have a little look to our map. So the headquarters sits in Munich. This is where the company has all its product management capabilities and sales management and so on. So it's the headquarters of Softing, also for Softing IT Networks. We have also two important branches spread over the world, in Knoxville in US to cover the American market, and the other major subsidiary we have is in Singapore. Singapore is our R&D department, which is providing us the high-end instruments controlled or driven by the Munich product management. London, Paris, Milan, Vienna, Shanghai. Reads a little bit like the fashion branch. No, it's this is a location where our sales offices are located to cover the sales aspect in the business for the whole world. What kind of products are we selling? On the next slide, you can see the main instruments, let's say, from our portfolio supply. And I don't want to spend too much time on this, just to give you a glance at the instruments we are selling and what area we are. So you see certifiers, you see qualifiers, verifiers, and so on. So what are we going to do today? Today we are going to talk about some fundamentals of data transmission. Only a short look to this. Then we're talking about dirt, dirt, which is one of the biggest enemies we have in data transmission on fiber optic networks. We will have a look what dirt can cause or what can do to optic and signals transmission. What else we're going to do? We're looking into some standards, normative background of cleaning and end phase evaluation. There are also standards in the background in the meantime, because it's such an important little aspect of the business. And then we see at last, we see our fiber optic microscope in connection with our test and measurement equipment, how these works together. So let's start with a few fundamentals in the beginning. Fundamentals is what do we use to transmit data on fiber optics? So most of you to know this, we are using multi-mode fibers, we are using single-mode fibers. What's the difference? Multi-mode, the core diameters are larger than in single mode. We got 50 micrometers, in the older system 62.5 micrometers as core diameters. The glass surrounding the glass core is called the cladding, which has a diameter of 125 micrometers, which is similar or is identical between multi-mode and single-mode fiber. In single-mode fiber, the core is not as wide as in multi-mode. We are talking here about the 9 micrometer core. So what's the difference in the application? So multi-mode fiber is typically used in short or mid-range applications within the building. That's typically the environment where multi-mode fiber is used. Because of the construction with this huge core with 50 micrometers, you get some dispersion effects, modal dispersion effects when pulses are traveling along. A light pulse is always divided into various smaller modes, as it's called, like you can see in the top picture here. And these modes traveling through the multi-mode fiber are using different ways. So there are modes which are quicker than the others, or almost slower than the others. At the end of the transmission line, my nice shaped pulse I sent in the beginning ends up in this funny waveform that you see at the end. Pulse is smaller, is lower in amplitude. We get loss on this. So, and it's difficult maybe for the receiver, first of all, to see the small impulse. The second one, if you send 2 pulses very quickly in a row on a multi-mode system, this modal dispersion might cause that the 2 pulses are just looking like 1 pulse, which is not good for the receiver. So the information which is received is different from the transmitted information. So that's not good. So multi-mode fiber is basically limited to smaller, to shorter ranges and to slower applications, let's say. On the single mode fiber is typically used for wide area networking to avoid these modal dispersion effects. The core is very small and you only get one single mode, which is transmitting the information. And this is not a few hundred meters, it goes over kilometers, 40 kilometers without a repeater, or even 100 kilometers without repeater. So it's a typically long distance application. And this long distance application needs especially very good laser sources with very high precision beams to be generated. So a single mode system is usually more expensive as a multi-mode system. So because multi-mode, the lasers or cheaper lasers you can use to drive the signal. So this is why it's pretty much separated the business: single mode transmission on long distance and multi-mode on short or mid-range distances. So that's the way it works. So just a quick repeating of the basics in the background. Then we have a few factors which are influencing this propagation of light. And we have effects called backscatter, also called relay effects. These relay effects are coming from particle inclusions in the fiber. So not all of the light we are trying to transmit down the fiber optic line is really arriving at the end. These particles in the glass, in the fiber optic, are giving some reflections, and this reflected energy is missing on the other side. So we have to take care not to generate too long cables with too much reflections, not to end up with too less power at the end. Then we have more major effects on the line as well. So if we connect, for example, two fibers together via connectors, then we got reflections, and these reflections are called Fresnel effects. Where are they coming from? They're coming from misalignment. So if the two cores of the fiber optic connectors are not properly focused to each other, so we get misalignment, we get also a lot of reflection back then. What else could this cause? Damaged or dirty end faces of connectors. So if dirt is in this connection between the two connectors, we have enormous reflection, and this is topic of this presentation as well. So you see that these are the main problem parameters we have at the moment, is the quality of this connection. What else could cause reflection? Insufficient termination in the plugs, or if the plugs are not connected properly to the fibers, that could be a trouble. Or another troublemaker of reflection is, of course, breaks in the transmission cable or something like that. So it's not working properly anymore. Let's have a little look to a fiber connector, how it's working and how it's constructed. So here's an example called the SC connector. As you can see on the right side, there is a whole bunch of connector types available on the market, and it's far more complicated than in the copper world. In the copper world, we are basically standardized on RJ45, but here it's far more difficult. So we got a lot of different connectors: FC, SC, LC, E2000, ST. So there are various kinds of connectors available, but in principle they are mostly the same construction. So there's a housing which is covering the whole. On the connecting point, there's a ferrule. This ferrule has different diameters, either 2.5 millimeters or 1.25 millimeters. In the center of this ferrule, there is the fiber, which is actually glass. And so we saw earlier in the slide, this fiber is constructed out of a cladding, which is surrounding the core. That's the construction actually of this connector. We will use these wordings a little bit later. How is a connection working? Let's have a look to a functional principle of a fiber optic plug connection. What you see, usually in fiber optics, you always connect two connectors together. So you're connecting male to male. So there is not too many systems, as far as I remember, which are female or a connection out of female and male, like we have in RJ45 on copper. We have a plug and we have a jack. In fiber optics, usually we have always two connectors, and these two connectors are connected through couplers. And as you can see here in this coupler, there's already one connector is fitted in. And so what's going on now? Now we connect the second connector. Here, a few wordings. There's a sleeve built in, a guide sleeve, to make a real good focus between the two connectors which are moving in. And the critical area between these two connectors is this point where they connect, actually, where they contact each others. If this connection is clean and is centered, then you get these fiber optic, they get the light beam very nicely through without big reflections and not with a lot of losses. So that's the optimum phase, let's say. And how to get to this optimum, there are three words which are used. The one is the core, the perfect core alignment. The other one is the physical contact, so each connector should contact the other one, and the pristine connector interface, clean connector. And this is when you have these three basic principles, then you get a clear and easy light beam transmission through this connection. So that's the best case, let's say. Let's come to the real world now. So let's introduce our dirt, as I mentioned, I call this. What makes a fiber optic connection bad? And the most critical thing is contamination. Contamination is the #1 source of problems in an optical network. So a single particle at the core of an optical fiber can cause significant reflection losses and even damages. So this is not very good, because if you have a damage, this connector you have to cut off and have to replace. Therefore, the visual inspection of the fiber optic connectors is the only way to make sure that these things don't happen. And you have to do it each time before you plug two connectors together. That's important. So here you got this picture, this example. So there's some dirt in between. And what size are we talking here? As you saw earlier, the core diameter in multimode is about 50 micrometers. And to give an impression what 50 micrometers are, a human hair is about of the diameter of 90 micrometers. So this core in there is about half the diameter of the human hair. And if you have a little particle of dirt and sits exactly on the core, you got this effect you can see here. The light beam is trying to travel through to the other connector, but this dirt is creating enormous reflection. And what you get is a very, very attenuated signal in the direction you wanted to have. The insertion loss is an enormous value on this connection. And this can be even worse. So on the next slide, you'll see an example that dirt can even destroy the fiber optic connector. So if you have a very, very hard particle between the connectors, and you plug these two connectors together and put some force in it, so it could happen that it's even breaking, or yes, breaking the connector. As you can see here, there was a very little stone between these two connectors, and stone and glass don't match very nicely. So what you get is pits, and what you get in the middle between these two connectors is you get an air gap, and an air gap is the change of the index of refraction. And change in index of refraction will always call a reflection. So what you get here is, because of this air gap stemming from this stone in between, you will get enormous reflection, and you get again enormous insertion loss. Your signal is attenuated very much. So only because there was a little stone between these two connectors. And the interesting effect is what we call is particle migration. So you got here a real life example. So what happens here? So you see this connector is a single mode connector, and this connector is a little bit dirty. And you see little dirt on this, or some particles on this, in the range between 10 and 50 micrometers, not very big. So what now happening is, for example, this connector you see here was a connector from a test cord. And what you're going to do when you do now testing and you plug this into a connector in a panel, for example, you connect it in, and what's happening, these dirts might get broken, and you get a lot of new dirt, or much more dirt, smaller size, but it's getting more and more dirty. And if you repeat this, so you're leaving the first panel part and move to the second panel port, the third panel port, you see that this dirt is spreading around, and you get some more and more migration on this, migration of the particles. So that's what we don't want. So what I mentioned earlier, before connecting, clean it, definitely. What are the effects behind this? If you now look to the performance of this kind of connection, you see each time you connect, the signal performance, the reflection behavior is getting worse. So usually you see these dotted line, the red dotted line, this is 55 dB reflection. That's typically for a single mode connector. And if you allow to get dirt on this, these reflections are dramatically raising up to here. In this example, we got went up to minus 40 dB. So when you got a lot of reflection, and these signals might, this amount of signal might be needed at the end of the link, and you don't have it anymore. So make sure before every connection, clean it. So, and on the next slide, I got a few examples of how this can look and how it will look on a connector as well. So dirt is everywhere, that's true. In the air, in the hands, closing connectors, there's always some dirt flying around, little particles flying around. And the typical dirt size is about 2 to 5 micrometers in size, which is invisible. You don't see it, what's going on here. And these single grain of dust can be a big problem, as we saw earlier, and you can destroy even the core of the fiber optic connector. And even new connectors can be dirty. So a lot of people believe when they take a new cable out of the box or out of the package, it must be clean. No, no, no. Always inspect the end face. There can always be a little dirt on this. Even when unplugging the dust cap, you suck into some air, surrounding air. You hear this noise when you take it off. And that moment, already a little particle can end up on your core of the connector and can hinder the fiber optic, the light transmitting, or it can even break in a later connection point. So here's the example. Here's the connector again. Now let's have a closer look to this one here, to the ferrule, and now see the fiber. And you see these are the little particles on it, only a few micrometers in size. You can't see it. If somebody's telling you you saw the dirt on the connector, no, I don't think so. If you do now some testing on this on these dirty connectors, and you can either test the insertion loss, which is going up, or what you can test is the reflection. So here on the next slide, you'll see a few examples of testing. Here somebody took 20 samples of cables and did some testing, and it did testing when the cables were clean, the connectors were clean. And what he did then, he put some finger oil onto the connector. So he just was using the finger and was guiding it over the tip of the connector. And this finger oil, what you see here, causing problems in transmitting the light. So maybe if you just look to the return loss, you see here is again this return loss, this dotted red line, which is the 55 dBs. The 55 dBs is the minimum requirement for the single mode connector, and you see very nicely when all these 20 samples are clean, you get very nice values above this dotted line. And just striking the finger on top of these connectors is causing that trouble on these limit lines you see, on the lines below you see, and we are going even down here to 20 dB of reflection. It's enormous amount of energy which is transmitted back. So make sure that you never clean a fiber optic connector just with the finger. That does not work. If we do the same now and have a closer look through an OTDR to this connector, what we can see here on the top is, here is a single mode connection. These are the two connectors which are connected together, mated together. And this is now a reflective measurement on the OTDR of this connection point. And you see you got enormous reflection here. You're down to 37 dBs of reflection. And you also get loss, an insertion loss. And the insertion loss is almost a dB you lose, just because of these dirt particles on the connectors. Cleaning these two connectors and reconnecting them, and you see reflection is rising up to above the level of the 55. And what you also see, the loss is only half of what we have before, just a few little particles on the fiber optic connectors. So, and there's some statistical value I found. It's about 85% of all network failures on fiber optics are caused by dirty connectors. I think that's something we can get rid of before we connect the connectors. What effects can this have now? So there is an example here that you've got some distribution system here. There's a head-end station. There are various local distributors, and these distributors are just feeding certain areas in a city, houses, and so on. So if you got a dirty connection in one of these distributors here, you might have a trouble. You might have a trouble between one customer and the distributor. That's fair enough. That can be solved easily, let's say. It's getting worse if you get some trouble in between, not from here to here, but you get it from here to here. You get it from the head end to the distributor. So this means maybe half of a city doesn't get any information, any internet connection anymore, because the contamination which sits in the head end is creating complete reflection and an outage of the signal. And this could be as worse as maybe only one little stone sitting on the core of a fiber optic connector. So it's a very serious topic. We got a few pictures then how it could look, how the different kinds of contamination can appear. And here are a few pictures made through the fiber optic microscope, and you see different shapes. What you see on the top row is this is a typical simplex fiber optic connection, a single mode connection you see here. What you see on the right side, this ribbon, this is some MPO stuff, MPO, MTP stuff, where you have maybe 12 fibers in a row or 8 fibers in a row, and that's the way they have to look like when they're clean. And you see down there are different pictures and appearance of different type of faults, and the easier things are the ones which is just dirt. Where it's more getting into trouble is pictures like this one here, where you see chips down or pits, where it's mechanically broken. You know, the core and the cladding is real glass, and it's very sensitive as real glass is. And if you scratch around with a hard stone on this glass, the glass is gone. So in this kind of in these situations, the only alternative is to cut off the connector and replace it against a new one. Here you see some remains of glue. Typical way to connect fiber connectors is to glue it in, and if the person who did not do it properly, you get too much glue on this. So these all effects you definitely have to try to clean. You have to see before, and then you have to try to clean them off. If not, replace the connector. So let's have a look to some standards in the background. Standards on end phase evaluation and cleaning. And there are one very prominent standard, which is called the IEC 61300-3-35. This standard clearly defines when a connector is really clean. So I can look through a microscope and can say, this connector looks clean. But is this the proper statement which allows me to say that this connection will definitely not hinder my data transmission? No, to make this more safe, they invented this standard, and when a connector is clean based on this standard, it's guaranteed that the application will definitely travel without a problem through this connection. And how this standard works, so you see there are two different approaches. One is for single mode and one is for multi-mode. You are defining 4 different zones, A, B, C, D, and the zones have a certain radii on this. And based on the zones, there is a certain amount of dirt which is maybe allowed, and amount which is too much. And you clearly can get a pass-fail decision on clear or not clear of the connector. That's important. So, where can you connect now these? What you see here, how to get to these pictures. How to get to these pictures, you see on this right side, left side picture, you see a little microscope which is connected to an OTDR in this case. And this is the way to generate these pictures and to make an automated pass-fail decision. That's important. And the automated decision is based on the standard and it gives you a clear indication. One point which is very important is what connector should you clean on the connection? Of course, you should clean all connectors. You should clean the connectors which are on the patch cores, as you can see here. And you should also clean the connectors which are in the panel behind the scene, let's say. So it's not sufficient only to inspect and clean the connector which is connected to the panel. Also have to make sure that the other connector on the other side is also clean. And this is also has an influence on what type of microscope you can use or you should use on this. I have a slide which shows you the various types of microscope you can use to have a look to these end faces, and it's starting with typical handheld microscopes. These handheld microscopes, it's a good start, let's say, but you only can look into connectors which you have an open access to this, so they can't look through a coupler and see the other connector in a panel. So they're good for testing patch cords and cables and this stuff, but they're completely not working for panels where the connectors are built in, except you would dismantle the panel and remove the connector from the background and check it, which is not very handy. Typically, what you use on site are these microscopes you see on this left lower side, the microscope connected to display or test and measurement devices that you can see here from a few examples. And usually the microscope also can be used on a PC, for example, if you do some evaluation on desk in your laboratory and so on. The laboratory microscope up there is not typically used in a field testing environment. It's really for more or less for fiber construction and creation of patch cord and all that stuff. So when you have detected that the fiber connector is dirty, you use the microscope. The next step is how to clean this. And when you talk to field technicians, what's your common modes to clean a fiber optic connector? You get sometimes a little bit funny answers. You sometimes hear, okay, wiping the connectors on the sleeve of the shirt is fully sufficient. Okay. Or, oh, if it's something on the tip of the connector, I just put it with my finger or wiping with my fingers over the tip of the connector and the dirt will fall off. If you don't want to touch it, so blow very vigorously over the end face of the connector to blow away all this dirt on this. Okay. Or what I once learned that is, I clean it with water. So I have a little glass with water next to me where I shake the connector, and dirt usually should be washed off. That's also a way to do. Or if it becomes more professional, you're using alcohol, but some people like to prefer the mild alcohol, some liquor on this, not the heavy ones. Or one of the other ways is to clean with paper handkerchief, very common. So just put it out of my trousers and use it, will work. Sorry, but that's all nonsense. And to avoid all this nonsense, there had also been now standards which are clearly defining what should be used, what is properly used for cleaning. And there are these two technical reports which are existing and trying to explain in that standard the importance of dust caps, influence on dirt. So what we went through now is in those standards it's gathered together, and also showing various tools and aids for correct cleaning of connector end faces. So it's definitely necessary sometimes to burn it into a standard to explain to people what is really professionally cleaning. So not the ways you have said earlier. So here are a few samples of the cleaning tools. Very common, you see on the top right corner is these one-click cleaners. Or the cleaners you see on the very left side, where the strap is moved on in there. Also down there is an MPO cleaner on the lower part of the picture. You got some pressured air to clean and so on. So this is professional cleaning equipment. Don't use your sleeve of your shirt, please. And if you do it right, there is a process defined, a simple inspect before connect. That's the topic of this presentation as well. That's the topic, how to do this, and it's very simple. Start with inspect. If you have inspected, make a decision. Is it clean? Yes or no? If it's not clean, no. You see this picture here, redo the whole stuff again, clean it again, inspect it again, next decision line, and do it maybe 2 or 3 times sometimes if you have to do this. Only if it's clean, connect it, not before. Any dirt on any cord you connect can really damage or cause real trouble to the other connector of the connection. So how does this look now in reality? Let's have a little look to the real world. So I got a slide here which is presenting our fiber optic microscope, Softing fiber microscope. It's just named fiber microscope, nothing special. So what it's doing, it's doing inspection evaluation of the fiber connector interfaces with one keystroke, and you got a turning wheel to focus the picture. And it's also building an automatic evaluation against these famous ISO IEC standard 61300-3-35. It's very easy to use this instrument and the fast analysis, and it's compatible with all our high-end instruments. It's compatible with the NetExpert qualifier, with the Wire Expert certifier, and with the Fiber Expert OTDR. So all instruments which are supporting testing and measurement on fiber are also supporting the fiber microscope, because it's such an important part of the business to have these end faces inspected and cleaned before the usage. We also offer adapters for the most common fiber optic connectors. As you saw earlier, there are so many different interfaces, so many different types of connectors, and you can change the heads of the fiber microscope to adapt it to the different connector types which are available. On the last slides, you see a few pictures as the look at this, as the usage of the fiber microscope is appearing on the instruments. And you see here is our NetExpert XG qualifier. Qualifier is qualifying fiber optic links, 10 gigabit Ethernet, 1 gigabit Ethernet, and also supporting the fiber microscope. So what you can do, adding to your documentation is the picture of the end phase, which is part of the documentation. So the customer is aware that in his fiber optic links, all the connectors were clean at the point where the measurement or the test has been done. So that's what you get from a NetExpert XG qualifier. If you connect it to the certifier, you also get some proper documentation of this. You see, it's also doing this analytics based on the standards. And if it's too much dirt or something is defective, you get fault. Or if it's working, it's fine. If the connection is fine, you get a report which is telling you, yeah, everything is good. You get it properly passed, the whole thing. Of course, the fiber microscope can be connected to the OTDR, our Fiber Expert. So this is the same. It's also using these 4 areas, A, B, C, D, to judge, is this connection clean or is it not clean? I think that's it from the technical point of the presentation. Let me see. Yeah, should be. Yeah, these 2 slides are a bit outdated. So thank you very much for the attenuation today. Just a little side aspect of all this testing and measurement, these end phase inspection and cleaning. I think I will ask now for Matthias if we got any questions so far. Matthias, are you still there?
I'm here. First of all, thank you, Alfred. We didn't get so much questions at the moment, so
Okay.
but we get definitely a few questions about you, the handout of this presentation.
Okay.
Yes, of course, we will do so. We will send it immediately if our network system is running again, because we have at the moment a little bit trouble in the company with our email system, so we are not able to send anything to receive and send emails right now, maybe today, but we will send it till end of the week. I believe we have your email address and we will send it. Normally we put it in to the documents folder, and you can download it during the web session here. But today it's it's slightly a special day, and we will send it to you at the end of the week. We've got some questions about cleaning. One is Alfred, what is your recommendation for a handheld microscope? Are the mechanical microscope useful for this purpose?
Yes, let's say it's better than nothing. As I mentioned in the presentation, maybe the question came earlier. If you have a handheld microscope, you can only check loose connectors which are not built in couplers or hiding away behind couplers. So you can test half of the show, which is better than not inspecting anything. But if you do it really professional, do professional acceptance testing, you have to move at a certain point to an automated microscope to be definitely in a situation to also see both connectors which are part of the connection.
There's a question about the microscope again. The question is, can I check the connectors of the measuring instrument as well?
Oh, yes. Yes, that's another recommendation. If you have a microscope like that, you always can see how your transmitting port looks like as well. So it's very important when you're using OTDRs, because you have to make sure that the first connector, the connector on the instrument, is always clean and not broken. Because on an OTDR, if the first connector in the instrument would have been dirty or with scratches, all the energy, most energy which is transmitted, should be transmitted over the line, is immediately reflected. And you can't do any real testing or measuring with an OTDR. So make sure also to use the microscope to see the own ports of your own testing device and to check the ports for dirt as well. Very good point.
Okay. And the last but not least is, what is it? Is it absolutely necessary to always clean the plug?
Yes, yes, clean everything, every connector, clean before you connect it.
Okay, that was all the question. If somebody want to address a question right now to us, you can raise your hand if you want. So there is the hand sign on the board there. If you raise your hand, we will open your microphone if you want to ask us something. If not, then you should be quiet forever.
That's not polite.
Speak now. Okay.
Okay.
Then I have to say thank you to Alfred. Alfred, your turn. Your last words.
Okay. Thank you very much to all attendees, and that's it for today. I will close now the webinar, and have a good time and stay healthy. Okay, bye-bye.